Lab 4, Spring Mass Lab. The objective was to examine the motion of a spring mass system in which the spring is oscillating in 2 dimensions, to create a computer model to demonstrate the 2-dimensional motion of the system using Newton's law and the energy principle. Then to plot the computer-generated motion and the position data from Tracker in the computer simulation and compare them. This comparison will reaffirm the energy principle that there is conservation of energy. The physics. Energy principle states energy is conserved if the system is not acted on by the surroundings. So we have our change in energy in this system is equal to the change in potential energy of the spring plus the change in potential energy for gravity plus the change in kinetic energy. Hooke's law will be used to calculate the spring's potential energy, which is 1/2 of the spring constant times the stretch squared. The gravitational potential energy is equal to the mass times acceleration due to gravity, which is g is 9.8 times the height. Newton's laws will be used to calculate the final velocity, and it's equal to the initial velocity plus the net force divided by the mass times the change in time. Kinetic energy is 1/2 of the mass times the velocity squared. The system has the origin at 0, 0, 0, and that's the attachment point. The calibration stick was set to 70 centimeters. The spring is hanging in the negative y direction with a mass of 0.402 kilograms attached to the end. The motion has an x and a y component. The video was uploaded and analyzed, and the data was saved in a .csv file, and then the position was plotted along with the motion of the computer to see if they matched. First, we had to determine the spring stiffness. We had the time period is equal to 2 pi times the square root of the mass divided by the spring constant k. The time period was from Tracker was determined to be 1.4566 seconds, and the mass was 0.402 kilograms. The time period was based on the y versus position data, not the x, because the x is just how far the spring was pulled to the side, not how far it was stretched. K is equal to 7.47 meters, newtons per meter. Determining the relaxed length of the spring, we've got force of gravity equals the force of the spring, so mg is equal to ks, which is the spring constant, times the stretch, and the relaxed length was determined to be 0.173 meters. Our system properties, the ball mass was 0.402, the position vector was determined from Tracker, and it was negative 0.10483 in the x and negative 0.6199 in the y. The ball's initial velocity was 0 in all directions. Okay, this is just the data that pulled in the position data from Tracker. And here we have some more initializations. Our delta t is very small. G is equal to 9.8. The spring constant was 7.47. The relaxed length of the spring was 0.172. And the end coding just has to do with the position of the spring, the direction it's moving, and the magnitude of our stretch. Calculating the energy, the first line is kinetic energy, the second is gravitational potential energy, and the third is the spring potential energy, and then you can just see the regular laws for those 3 different energies and how they're calculated. Now, this is our calculation loop. While time is less than 9.212 seconds, and in brown, you can see the different potential energies equaling what was defined above in the last slide. In red, you can see the different forces acting on it, the force of gravity, and again, it's a vector component, but it really only has a y component in this direction, and that's negative ball mass times 9.8. You can see the force of the spring, and then the net force is the force of gravity plus the force of the spring. So that's our total net force, and then in orange, you can see the velocity is equal to the initial ball velocity plus the total net force divided by the ball's mass times delta t. In yellow, you can see the ball position is updated by taking the velocity times the change in time. In green, you can see updating the spring, and you've got L, L hat, and then just the stretch. And in blue, you can see the change in the energy. So you're calculating delta K, delta U sub G, and delta U sub S. This last part in purple is just the graph that shows us the change in kinetic energy, the change in potential spring energy, the change in gravitational potential energy, and then all of those 3 added together, which is our delta E, and that should be straight across with no changes. And here's the simulation. And you can see in blue is the kinetic energy, red is this potential energy of the spring, green is the gravitational potential energy, and yellow is our change energy, which is a nice and even and level all the way across, which is what we want to see. Now, in the next one, we change the plot a little bit so that it's just the position of the computer model versus the position data from the video. And you can see at first that they're fairly close together. There are some gaps, but I think that's probably due to the mass of the spring not being taken into account in our calculations, and the fact that drag does have a existence in the real world, and so I think it gets worse and worse as the time goes on due to drag. So overall, the energy principle was upheld, that energy is conserved. It's just that in our computer model, drag was not taken into account, and the mass of the spring was not taken into account.